Hello, my name is Jonathan Apostle, and this is my second lab report for Physics 2211. The purpose of this lab was to record an object falling at rest from a given distance in Tracker, comparing it to two additional models, one which accounted for drag force and the other which did not. Some key principles and models to know are first Newton's second law, which says that acceleration is proportional to the force applied to an object. The second one is the kinematics equation for free fall, which we will especially use for Model 3, which shows constant acceleration. Some important forces to know are first, the force of gravity, and also the drag force, which we can't quantify. The terminal velocity is the force of gravity when it's equal to the drag force. Another key facet is momentum, which says that momentum will be equal to the net force of an object multiplied by the change in time. The result for this lab was that the model which included drag force was closer to the observed model than the one that did not. So now to look at my main physics ideas, more specifically the equations and also the reasoning for why I use these equations. First, I have the position update formula, which is a way to correlate position with velocity. Also, the velocity update formula, which is a way to correlate velocity with the forces, more specifically the drag and the gravity forces. Also, I use the momentum equation, and this is mainly just to show that the force changes when time changes. Also, there's the drag force, which is part of the net forces of the object, which is present in the models 1 and 2, the observed and the computational model, which accounted for drag. Also, there's the free fall equation, which is the principal force of Model 3, which is gravity, so the velocity will be linearly decreasing. So to briefly look at my main physics ideas, more specifically the figure and the system and surroundings, I have my paper boat, which is basically just a folded piece of paper onto itself in order to create a lot of drag force. I have the gravity, which acts on that paper boat, and then also the force of drag, which is not present in the computational Model 3, which is the one that specifically did not account for drag. Now looking at my initial conditions, first off, my time is 0 to 0.6 seconds, and the height of release in Tracker was about 0.15 meters, and the position after release, so basically after the object had dropped, it was negative 0.763 meters, and the B value I obtained was 0.17, and I basically got this from just trial and error on GlowScript. So as you can see here's my paper boat, which I dropped from this height, and I just clicked on each point where the boat was. An issue that I encountered was that the paper slightly moved in the X direction, but I'm going to talk a little bit about that later just in the discussion section. Alright, now looking at my GlowScript code. First off, in line 36, I showed the mass of a piece of paper, and this was obtained online. In line 40, this was the initial height, which was 0.15 meters. On line 45, this was the time increment, which was 0.033 seconds. This was gotten off of Tracker. Line 57, this is when B is 0, and obviously this is the one where no drag force is for this model. On line 74, this is where only the force acting on the object is gravity. Then on line 78, this one updates the ball's velocity. And then on line 81, this is which updates the ball's position. Alright, now looking at my computational model which accounts for drag. In line 64, I updated B as described earlier. And then in line 71, the force of drag is different than the previous one. And again, I derived it from the drag equation that I described in the equation portion of the lab. And the only thing that's different here is the existence of the drag force. And this in turn will change the net force. So in line 74, I just updated the net force. So after looking at my different computation models and my actual model, I plotted the time in 0.6 seconds and position. As you can see, the position of the computational model, which accounts for drag, is more similar to the observed model than the one that did not. For my discussion, some similarities and differences that I observed were that for the observed model, Model 1, it appears to be more similar to the model with drag force acting on it, Model 2. This can be seen from my spreadsheet data. Yet they are not entirely the same. This is probably due to a difficulty finding the exact force of drag acting on the object. So basically, if I found the right B value, I think I can get them to be a little bit closer. Some possible sources of error for this experiment were that the movement of the object was slightly in the X direction, meaning that it was not entirely vertical. Again, this messes up the value because it's starting to move more diagonally. And again, it was difficult to track the center of mass in Tracker. Now looking at the what if questions. For starters, which model will predict the terminal velocity? This would be the model with the drag force. And this is because the net force and acceleration will be 0 at a certain point, meaning that the velocity will be constant. What if the model was initially thrown downwards? Well, the terminal velocity would be the same, it would speed up or slow down to match the terminal velocity, and it would basically reach a limit. In the computational model that I did, it's about negative 1.7 meters per second. So for starters, the one with drag force, but it wasn't thrown down, as you can see, it reaches a limit of about negative 1.7 meters per second. However, for Model 2, the one with drag, and it was thrown down at negative 1 meters per second, it too has the exact same limit that it reaches.